I'll begin. Good morning, everyone. Welcome to today's webinar, Nonlinear Finite Element Analysis Using Advanced Engineering Software. My name is Dikshit Babu Nepal, and I'm the Managing Director at Excel Engineering Research and Education Center, and I'll be the moderator for today's webinar. Thank you all for finding time and visiting today's webinar. Now, before we begin, I would like to request the Chairman of EEREC, Sujan Tripathi, to chair today's webinar. Thank you, sir. Well, our keynote speaker is Dr. Prachan Pradhan, the Associate Professor of Department of Civil Engineering in Kathmandu University. He has been actively working in the field of infield masonry frames, structural dynamics, earthquake-resistant design, and retrofitting of structure. Many of you may not know that Dr. Pradhan also received Nepal Vidya Bhushan Class K in 2015. He has more than 40 publications and has already served as a member of editorial board in more than 10 journals, which includes Engineering Structures and the American Journal of Civil Engineering and Architecture. We want to tell you how proud we are of you for your outstanding achievement and would like to welcome you to this webinar. Thank you, President, sir.
Thank you very much. Thank you very much.
Next, it's a great pleasure for me to introduce our speaker today, who is going to talk to us about the capabilities of finite element software. Our speaker has spent his research career at Thammasat University and University of Melbourne. He is an award-winning PhD candidate who has specialized in finite element software operation for more than 4 years. Please join me in welcoming Rajendra Bohra.
Thank you, Dikshit.
Thank you, Rajendra Bohra. Now, without any delay, I would like to request Engineer Rajendra Bohra for his presentation. So
Okay, I share my screen.
Yeah.
Okay, hope you can see my screen.
This looks fine. Okay, you can start, Rajendra.
Okay, good morning, everyone, and welcome to the webinar. And thank you, EEREC, for this platform for sharing ideas and all the participants for your time. And today I will be presenting on nonlinear finite element analysis using advanced software. And the main content of this presentation are introduction of finite element method and some software packages that we have been working on FEA, and some general, very general working steps in FEA packages, and to visualize these steps, an example of simply supported RC beam, and finally, several multi-physics simulation examples to show scope and capabilities of this nonlinear FEA program. So in the first, FEM is a computational method that works based on the approximate solution of boundary value problem. And the main working principle of this FEM is discretization of the domain of interest. That means if we have an object or the problem, we discretize this object into number of finite elements, and each element consists of several nodes at its end, and we know the solution at the boundary, and based on that solution, we interpolate solution to the other nodes. So in finite element, basically, we deal with nodes, and these nodes make element that we can visualize from this picture, and combination of several many elements make a structural part, and assembly of these parts make structure. So for part and structure, maybe this picture would make you clear. For example, in this picture, this water is one part. So this embankment can be considered as another part, and the soil can be considered as another part. Again, in this example of a reinforced concrete beam, we can treat concrete as one part and stirrups as one part, and the longitudinal bars as one part as long as the longitudinal bar have same diameter. So generally, a part is a structural component that has same geometrical and the material properties. So regarding these elements, we have basically three kinds of element: beam element, as in the reinforcement bars, and then steel element, plate, two-dimensional, and the solid elements. So, in this webinar, I have not covered about the theoretical aspects of this element type and different interpolation functions. Mainly, I have covered about the practical aspect of finite element analysis. So, if we talk about the advantage of finite element analysis, according to IEEE, there are basically 6 the main advantage. The first one is by using finite element method, we can model any kind of the complex geometry and the irregular shape that we can also visualize from this picture. And also by using finite element method, we can get the result with a good accuracy so that we do not need to test our physical prototype, which obviously saves time and money. And also we have many short-term and long-term time-dependent simulation options, different kind of boundary conditions in FEA software package. And finally, we can visualize our result in terms of different interacting environment like photo, video, graph. So it is really easy to understand what is happening in the structure if we simulate by using nonlinear FEA programs. So next, regarding the field of application of these nonlinear programs, generally we can use them in all the sector where we deal with the stress and strains. So it covers all the aspects of engineering like civil engineering, mechanical, aeronautical, biomedical, almost all those areas of this engineering. So if we typically talk about our structural or civil engineering, we can use it to analyze building, bridge, or typical structural component like beam column joint only or beam only, or interaction between fluid and structure and different other aspects that we'll see in the later slides. So next, these are some of the FEA software packages, and I divided this packages into two columns. In the first column, softwares like SAP, ETAP, SAFE, STAT Pro, and in the second column, I put Ansys, Elestina, Diana, and Mark, etc. And the main difference between this software, if I talk about the performance evaluation, these software packages are, if we talk about the positive part, they are relatively easy to use, and they require very less computation time and resource. For example, we can solve a 4-story building model using ETAS in less than 1 minute. That's really a good part of it. And also it gives good accuracy for the global performance. And one most important part is in most of these software packages, we already have the design code. So they are really suitable for design of standard or the conventional structure like reinforced concrete frame, masonry. But when we have to deal with the highly irregular structures or highly complex geometries, then we cannot model with their grid system. So we need to move to this little bit advanced software. Also, when you want to analyze the structure with non-conventional material, let's say like fiber reinforced polymer or some composite section, then again, they are not suitable for that kind of analysis. So we move to this software package like Ansys, Elestina, Abacus. Regarding the capabilities of this software packages, more or less, they have similar capabilities. But in this webinar, I have been working in Elestina. So, most of the simulations are based on Elestina. And if we talk about Elestina, this is a general purpose finite element code, and it is capable of simulating almost everything in the world. So all the complex multi-physics scenarios in the world are can be simulated in Elestina, and these are the major capabilities of Elestina. And we can simulate from linear static, non-linear dynamics, crack propagation, real-time acoustics, almost everything in the world. And if we talk about some beautiful feature of Elestina, we can couple two multi-physics scenarios. Like we can, in the same model, we can consider structural and thermal part, or structural and acoustic, or all of them at the same time. And also, if something is not available in Elestina, we can create by ourselves by scripting. So it is really useful in research. So now we move to the next section, general working procedure. And these steps are not only for Elestina, but they hold true for almost all software packages. So we have, in general, 3 steps when working in FEA packages. The first one is pre-processing, then solver, then post-processing in general. So in generally, the pre-processing is the phase of preparation of the model. So in pre-processing phase, we create geometry, then we mesh, assign appropriate material model, and apply boundary condition and load. So after preparation of the model, we pass that model into the computer. And the solving phase, we don't need to do anything, just everything is done by computer, and it gives output. And that processing of that output is the post-processing phase. And for this pre-processing and post-processing, each software package has its own user interface. And for that, Elestina also has its user interface, and that we call LS pre-post. And this is the graphical user interface of Elestina. And here we can do many things, like we can prepare CAD for model, also welding option. We can input different finite element, and it also support ASCII and binary files. And regarding the output, we can get the result in terms of image, movie, XY plot, or different other standard interactive environments. So now after that, I would like to move to this section. So mainly these are the steps that we carry out in the pre-processing phase. And the very first step is geometry. So we just replicate the real structure in the computer in the form of CAD, and then we divide them into finite elements that's meshing. And when meshing, generally we prefer fine and regular meshes, but one problem here is if the mesh is really very fine, the computation time will be very high. So we usually do the mesh convergence study to find the optimum mesh size here at this step. And after that, we need to select the appropriate material model, or also called that constitutive material law. And the main function of this constitutive material law here is to define the relationship between stress and strain at different loading state in the element. So initially, we know all the elements have linear behavior, but in the non-linear range, different material have different behavior, like some are from brittle behavior, some has strain hardening, some softening. So when selecting this constitutive material law, we should have some knowledge in mechanics of the material, how the material behaves in real world, and also the theory of the material model in that software package, so that we can select the appropriate constitutive material law. And regarding this, in LSTINA, we have more than 270 laws for the material model, so it covers almost everything. And next is the boundary condition. Regarding this kind of support-based structural boundaries, we can define in terms of different degree of freedoms. But also, in addition to these support-based boundaries, in FEA, we can also treat reflective, fluid, and other continuum domain easily. And next part is, as we know, in the structure, we have to deal with different or many structural parts, and they interact differently. And we can generalize them into two types of interaction. The first is the contact, and second is the constraint interaction. In the constraint algorithm, the structural parts are connected by their external surface, and we can treat them with friction, cohesion, or something like that. And generally that is defined in terms of contact algorithm. But when one part is embedded in other parts, something like reinforcing bar in concrete, then we need to treat with the constraint algorithm. And in the constraint algorithm, generally we define their bond slip law, something like this. Different plot force and displacement relationship are defined in this bond slip law for the constraint algorithm. And finally, we assign different load. And as we know that the main function of load in the structure is to excite the structure to respond. So we can either apply the real world excitation scenario, something like for the earthquake, we can shake the ground and it automatically apply the lateral force to the structure, or we can simply apply the equivalent lateral force for the earthquake resistant structure analysis. And same scenario you can imagine for the blast as well. Either we can simulate the actual detonation scenario, or we can apply the equivalent pressure history. And finally, at the end, we need to define what we want from the model, like what it should calculate for us, something like force, displacement, rotation. After setting this database, we run the model. And while running, most of the code have two features, like for solving the static problem, we prefer implicit solver, and for the dynamic problems, we prefer explicit solver. We need to be clear about that, what kind of problem is we're going to simulate. And now to visualize these steps, okay, let's see an example of simply supported RC beam, and this is the detail of the cross section, and the beam is around beam is 2 meter in length, and it is bottom bar 20 mm, top bar 12 mm, and the stirrups are of 9 mm. 100 mm spacing is 100 mm near the support, and 150 mm in the mid span of the beam. And the first step, we create the geometry for all the components. So concrete, this is concrete, and we create everything like all the rivers one by one, and then we mesh it into appropriate size. And here I have used 8-node brick element for the concrete and beam element for the rivers, and I have assigned different their appropriate diameter. If we see here, in just such a small structure, I have 4 different parts, like concrete is one part, and this top bar is one bar, bottom bar is another part, and this stroke is another part. And I need to define the interaction for them. And after that, this is the constitutive material law or the material model that I adopted for this nonlinear simulation. So for concrete, the linear part is mainly handled by the modulus of elasticity here, and the nonlinear part is handled by two parameters. This d is the damage parameter, and fc is the initial compressive strength, and the d depends on the stress and strain developed in each element of the concrete. So it will be averaging in each element in the 6 direction for estimating this nonlinear behavior, and major input for this continuous surface cap model for the accurate simulation of concrete are compressive strength, Poisson's ratio, density, tensile strength, fracture energy, etc. And sometimes we may not have this all data, so we can estimate this fracture energy, tensile strength based on compressive strength as well by following the standard. We have many formula in standard to estimate these parameters. So next is the material model for the steel, and in this simulation I use bilinear model by using this piecewise linear plasticity model in Elestina, and it simplifies the tensile behavior of the steel in bilinear idealization. First, it will be governed by modulus of elasticity, and after yielding, it will be governed by the hardening or the tangent modulus. So major input here are modulus of plasticity, this hardening modulus, yield strength, and also mass density and Poisson's ratio of steel. In this simple problem, I constrain the rebar in the concrete as a perfect coupling, so they won't slip at all at any loading state, but it may not be valid for all the problems. So finally, in this problem, to get the continuous load deformation curve, I applied the displacement control load. The main benefit of applying this displacement control load is we can get this load deformation curve continuously, but in case sometime if we apply the load control after this point, the peak point, it is really difficult to control the nonlinear behavior. It fails abruptly if we increase the force after this point. So it is really good to apply displacement control load when you want get a continuous nonlinear behavior from the model. And finally, as this is a static problem, I use the Elestina implicit static solver to solve this problem. And if we see at these are the main results. So to visualize this damages, let's flexural damages, I use maximum principal strain, and this is the load deformation curve, and graphical representation of stress and stress can be seen here. And the most important part here is how do you know these results are correct? Because software may not give the correct result all the time, so we should always verify and validate our model appropriately. And there are so many methods for validation and verification of the model. So if I follow this book, according to this book, generally verification deals with the mathematics or the concept. For example, for the static structure, one way to verify our model, a simple way maybe like force reaction balance check, or sometimes for the dynamic problem, if momentum and energy are conserved or not, that way we should see its concept. But also for the validation, generally which deals with the physics or the real world scenario, the most widely followed method for the validation is experiment. If you see, this is the same beam that I saw in the last slide. So we can compare like what is the response in from the finite element and what is the response from the experiment. So we can compare and validate our model if possible. And this is the most widely followed method in research for validation of our model. But sometimes we may not be able to carry out the experiment for the large scale structure. In that case, we prefer some kind of pilot experiment, or we follow other theoretical approach to validate our model, like mesh sensitivity, if constitutive materials are working appropriately or not. So if you are working in this field, maybe this book may be appropriate for you. Like, if you are working in computational science and engineering, really good to know about the different technique to validate and verify our models. I also took all the methods from this book actually. So next, okay. So now we move to the next section, scope and capabilities of nonlinear FEA program. And here first example I present is analysis of a non-ductile RC column. And this is a general test setup for a column. If you are not familiar, usually when testing or simulating the performance of column, we construct the column over a base block and we formally fix the base block at the base, and we apply the lateral load and the gravity load from the top. And these non-ductile structures show very heavy damage under cyclic load, and they are really difficult to capture with the normal programs. And we need really advanced program like LS-DYNA. And if you see here, in LS-DYNA, we have some features like element erosion, and by using this kind of features, we can accurately simulate the this spalling of the concrete and buckling of rebar, many features. So it's really good to simulate this kind of non-ductile structure in LS-DYNA. And next example here is analysis of a post-tension RC beam column joint, which also under lateral cyclic load. And if you are not familiar again with the testing of the beam column joint, we test the beam column joint only. We only consider the point between the the portion of the structure between the point of inflection, and we apply this roller support at the end of the beam and hinge support at the base of the column, and we apply lateral load and gravity load from the top. And we can see how accurately the LS-DYNA has predicted the hysteresis behavior and damage on the concrete here. And the most important part is pre-stressing. Usually this pre-stress should present in the structure before this external load, lateral and vertical gravity load act on the structure. And for simulating this kind of behavior, we need some special features like dynamic relaxation in the software, and they are present with nonlinear FEA programs like LS-DYNA. And next example here is about a composite structure, and we have two kinds of structure: precast concrete and the cast in situ concrete. This is a typical beam column joint from this structure, and here what we want to simulate is under the lateral cyclic load, how much is the slip between this cast in situ concrete and the precast concrete. So generally this kind of analysis are not possible to do with the normal programs, and we have to deal in the different kind of contact and for this interface. So we need to move to nonlinear FEA, and by using this kind of program, we can also predict like damage pattern and different responses like hysteresis, displacement, ductility, load transfer mechanism, everything. Actually, this was a part of my MSc thesis, and if you are interested in this system, you can follow. They have already been published, and you can follow my publication. And next is this is an example of shear wall under lateral cyclic load, and here we have applied the lateral load from this part, this in the in-plane direction, and we want to investigate its hysteresis behavior and damage in the shear wall, the concrete damage at different loading point, and also the rebar buckling and rebar fracture. Here you can see that how accurately the program is predicting the hysteresis behavior at different stages, and also what is happening in concrete and the rebar at the same time. So this kind of post-processing feature also helps us to visualize and interpret our results so easily. And the next example here I have is this analysis of steel frame. And so far, all the examples were based on the lab test, and this example is quite different than the previous examples. Here, this is a steel frame, and we have applied the seismic time history at the base, and we want to see how this bracing work and what is the ultimate collapse mechanism for this structure. Actually, I'm not sure about what was the seismic time history for this one, because I didn't simulate this structure by myself. But looking at this failure mechanism, it seems very high. And the next example here I have is a simulation of a mosque or masonry structure, and we want to see how this structure behaves under seismic time history. And in modeling, the brick has been modeled with the constant stress 8-noded brick elements, and the contact between each brick is idealized with the tie break contact model. And this is the seismic data in all three directions, and we can see how we can see the output in the program. And now I move to another example. Another is of road safety structures. So As we know, these road safety structures are really important for minimizing accidents and probable casualties. And we analyze this kind of road safety structures under the impact of the vehicle. So this impact of vehicle lead to very heavy damage or the very high deformation. So we cannot treat them with the normal kind of programs. We need nonlinear FE, and they should be quite advanced as well, because it is really difficult to simulate this level of damage using the program. And as far as I know, most of the simulation and papers on this kind of simulation are based on LS-DYNA, maybe because of its large material database and other features. And the next example here is analysis of railway structure. As we know, in railway structure we have several components of different material like steel, rails, then concrete or timber, sleepers, gravel, and subgrade. And at the same time, different kind of load acts, something like wheel load. At the same time, this rolling of the wheel causes friction and heating, and also the continuous loading and unloading causes fatigue. So we need to consider this multi-physics scenario at the same time. And for this kind of simulation also, we need to move to the nonlinear FEA programs. And for this kind of typical railway analysis, in the literature, I found two ways. One way, we can model the complete everything, like we start from subgrade to the cart and apply the real excitation scenario. And in the another case, we can simplify it as in the beam column joint or column only, which is our interest. We can separate the structural component, apply the appropriate boundary condition from bottom, and apply the load to see the response. And next example here I have is a typical analysis of hydraulic structure. And the most beautiful part of this LS-DYNA is we can couple both fluid and the structural part, and we can see the response of structure and the fluid at the same time. Something like this is the deflection of hydraulic gate, and at that time what is the velocity and pressure in the fluid. So it really makes easy to understand the problem and accurately simulate the physical behavior of the structure. And this problem was typically solved by using the SPS smooth particle hydrodynamics, so that it is more accurate for the fluid problems. And now I move to another example. This is a typical example of drilling mechanics. So we can do this kind of simulation as well in LS-DYNA. And in this example, I think typically useful for in civil engineering analysis of rock during tunneling, and which may be useful for predicting different stress and strain on rock. And also later it can be used for the analysis of support and other parameters in tunneling. And one more example is about the defense structure. And this small structure is called the earth cover magazine. As I used to work with the Royal Thai Army for analysis structure, I typically take from that one. So this structure are mainly used for the storage of explosive, and we analyze this structure based on the accidental scenario. Something like if one of the structure explodes, it should not harm the other explosive in other ECM, so that the chain reaction is prevented. So this is a typical analysis scenario of earth cover magazine. So we just take the two structures and cause the explosion in one ECM and see what is the response in another. That's the design philosophy for this earth cover magazine. And one more example from the defense side is analysis of soil blast scenario. And this scenario may be useful for two typical cases. One is when we analyze the structure or the vehicle under this improvised explosive devices, or simply we call it ambush. Also, same kind of analysis philosophy can be used when we estimate the rock or soil defragmentation using explosive in construction. We can estimate what amount of rock will be diffracted, and what will be the depth and the diameter of this depression in the soil by using this kind of modeling techniques in LS-DYNA. And one more feature of this LS-DYNA is we have a facility to create the new topology and shape. So this is a typical example I did for the impact load. This is the beam, and I have formally fixed these two in. And what I want to do is get new topology so that the reaction at this 2 end is minimized, and the deflection of this beam should not cross this criteria. So based on this simulation at around 40 iteration, I get this kind of topology, and you can see the response on this left-hand pictures. So the reaction has been significantly reduced, and also it has satisfied my deflection criteria. It didn't let the central deflection cross 110 mm. Actually, that's all. And in conclusion, we can use these multi-physics simulation programs in almost all the sector, like industry, research, academia. Also, the one most important part is before we present our result, our model should be appropriately verified and validated. And thank you for listening. And these are the references. Most of the earthquake and the blast problem were done by myself, and so you can follow my literature if you need more information on that. Okay, thank you so much for listening.
Well, thank you, Rajendra Prasad Bohra. That was really an interesting presentation. And for those of you joining us right now, welcome. And today we'll have 2 presentations, and you'll have the opportunity to submit text question to today's presenter and keynote speaker by typing your questions into the chat panel on this interface. You may send in your questions at any time during the presentation, and we will collect them and address them during the session. So now may I request our keynote speaker, Dr. Prachan Pradhan, to begin his presentation. Thank you.
Okay, I dropped my.
Let me share the screen. Okay.
Yeah, sure, sir. You can share your screen now.
Yes, I'm trying to. So I think it's visible, right?
Yeah, we can see it, sir.
Okay, welcome all. The chair of this program, Susan Tripathi, and the moderator, Dixit Nepal. And of course, the first presenter, Rajendra Prasad Bohra. Today, I'm giving a little brief speech on the computer-aided design with FEA approach for structural engineering. Well, most of the things that are very useful and the applicable and the application methods have already been discussed by Mr. Bohra. I would just like to point out few things which are very general, but maybe quite important to the civil as well as the structural engineers. Okay. This is the poster. And since Mr. Bohra's introduction has already been done by Dixit Nepal, is a little bit of thing that I have written over here, that he is a PhD candidate in the University of Melbourne, and he indeed gave a very nice explanation of how to use the software and what are the relevant softwares that are useful for different, different problems. You can't use the software in every aspect, so you have to choose these softwares like that. And he did his master's from Thammasat University, Thailand. Also, he did his bachelor from IOE in the year 2015. And I am glad to see that he has got some 12 publications and also had practiced a lot as a civil engineer. And now his research was based in the finite element applications in structural engineering. So here, firstly, I would like to talk about the computer programs and uses in structural engineering. Now, Mr. Bohra has already shown you different softwares, and also they were categorized in which aspect, in which conditions you should use them and which condition you should not use them. So to name them, I have also given some names over here like SAP 2000, STAT, Pro, ETABS, RISA, and all these kind of things he has already mentioned earlier. Now, the question is, what do we learn in undergraduate? That's the main problem over here. the basic thing is in the undergrad, the students, they learn the fundamental approach, the classical approaches. But when it comes to do their masters and in the real practice, we never use it. We seldom use it, in fact. That's because, you see, it is written there, which actually makes engineers know what and how structures behave as per the theory of structure. But when you really need to do it in a practice, there comes a problem. That is the problems that you have to deal with, you have to solve with. You cannot do it immediately. And when you are a practitioner, when you are a consultant, or a student or a researcher, you may have very short time to do all these kind of calculations. So we just have to understand that the softwares that are available to us, they are like calculators for us. For example, some time earlier, if there was no calculator, also even that time, structural engineers used to be there. They used to do all the calculations manually, and they used to, complete the task with a little longer time. Even if I remember what I did when I was doing my practice in the late 90s, I used to have a lot of time. I mean, the project duration used to be quite long. So we could, because there was a constraint of softwares and we only had 2D softwares. So those times, even the clients or the owners, they used to ask us, okay, you may take time for this much time, so that we can complete the work, taking a long time. But nowadays, there is no time for such things, because the softwares are already there with the accurate ones and very fast ones. And even the supercomputers are there now to compute large calculations also. So all the fundamentals that the students learn in undergrad, they are the background. If you do not know all these things, then the problem is you don't know whether your answer is right or wrong. Because from the basic calculations that you do from the undergrad course, whatever you learn, with a little bit of idea, you can even find out whether your answer is right or wrong. Like Mr. Bora already indicated, there is a book to validate whether your answer is right or wrong. That is one part, but the other part is you can even come to a very lower level and make yourself clear that your answer is right or wrong. And that is from the undergrad fundamental level. So this is why we should not forget that only learning software is very good, but to use the software in a very appropriate manner is very essential. Okay. So here again, I have written this thing twice, like white software with FEA. You can see engineering practice needs stipulated time frame to perform the job or the research works that I've already explained. The theoretical approaches provide only maximum values of responses. Like when we used to do undergrad studies for bending moment, shear force, axial force, whatnot, then what we used to get? We used to get the forces, the responses only at the nodes or in the center, midpoint. But that does not serve for the researchers. And that also may not be good enough for not only for the researchers, but when you have to do some calculations of typical things like shear wall, if you want to find out the strains at every level, every point of the wall, then it is quite difficult with the general method. You cannot perform it. So that is why the softwares are there. And then these softwares will be able to give you responses anywhere within the structure. That is the advantage of this finite element method, because Mr. Bora also indicated there are, you can discretize the elements. If there is a beam, you can discretize it into number of points, and you can get the results in every point. Of course, you can do that also by doing basic mathematics. For example, in basic mathematics, we used to take x as a distance, and then you do the calculation for that x point. But you can get that result for x one time for one time. But again, if you change that x, you have to do it again, taking another x1. Again, you do the calculation. So it takes quite a long time to get the similar result. That is the reason why this finite element approach gives you this facility that at one instant, you get very correct answer in a very short time. So large calculation is not possible to redo over and over again with maximum accuracy. This is the advantage of FEA over these basic fundamental approaches. And of course, the precision results we have already discussed. Now the feasibility to do due to computer facility, how it became possible now. So in the beginning, this finite element analysis was considered not feasible. Till the computer age started, though it was developed by engineers in the 50s, let's say mid 50s, to address the structural mechanics problems and related to aerospace and civil engineering. But after the development of computers, the finite element method, this revived, and large computations were possible in short time. After 1969, it took some pace. Later, with powerful computers, the FEA took full swing. So people, the mathematician, they started using the finite element method, finite difference method, all sort of methods like that. And at one stage, it was not popular because, again, there was a large volume of calculations needed to be done. Even when we teach finite element method in master's degree, we only can make them solve for simple beams, simple elements by manually. We cannot solve all these problems by manual using the finite element approach because there is a large computation. And this computation problem was solved because the computer was there. So after the availability of computer, and now to mention the supercomputer to calculate large volume of mathematics in a very short time, these computers are giving us every possibility to solve these problems. So that is why, again, this finite element method came revived and it became very popular. So let me give you one example. It's a very simple example because I always want to give examples with a very simple things so that it will be easy to understand and then implement also. In the first figure, you can see it's a full infield frame. So there are two beams and two columns and the wall is there. So if you want to model these things, normally for the structural engineers, what do? We don't even put the infill in the frame and we simply make the skeleton and then start doing the analysis. And you get the bending moment, shear force, and all these values in a frame. And of course, you take the load of the wall as a UDL. But when it comes to lateral loading, the response that actually is provided by the wall is different to that of a bare frame. So considering this fact, the softwares, they started getting improvement. They started improving their user friendliness for, okay, let's start doing for the wall also. Then what they did, okay, they said, okay, we'll put shell element. Then once we start putting the shell element, like shown in the right side, figure in the right, you can see there are a lot of meshes done. So with these meshes, the lookalike of brick wall was established. But when the lateral load was applied in this frame, inclusive of the shell, what happens is every mesh will be considered as fixed to the columns and the beams on four sides, which is not, if it is not the reality, then the response will not be exactly to what we expect. So to make these kind of corrections, people need to know more about the finite element approaches, finite element knowledge. So which software can do this, or which method you can manage to get the most correct, most appropriate result. So to seek this kind of problem, we want to know that the finite element approaches are there, but we must select the proper tools. And also, we must also know how to model these properly. Okay, so here I have written modeling approaches for result. SAP 2000 performs as shell element, but there are constraints according regarding real behavior. However, practically infills are ignored in modeling due to complex. And again, if you do start doing bare frame analysis, then you see it's done for all types of frame, but this does not represent real behavior. This I have already explained. Then, if you want to do some researches, then you must identify or know how actually the real behavior happens. For example, if this is a wall, then the wall is connected to the frame, a concrete frame, with these void parts, this void part, where there is possibly mortar only. This mortar is not brick. So the behavior of brick, the behavior of mortar, they are different. And also the behavior of mortar is different to the concrete. So these materials are different. So when the materials are different, their value, their stiffness, their strength, their Young's modulus, everything is different. So if everything is different and the behavior during the lateral force is also different, then that should be incorporated in your model. For example, this one model I have taken as enlarged form of this joint. Then I have placed K over here. That means the mortar will possess its own stiffness. So if you know how to connect this mortar with the concrete pillar over here, and of course it has to be done with everywhere all around, because there are two beams and then two columns. So you should be able to connect these, and you should know what is the value of K stiffness. And if you know this, then you can directly apply in the software, and the software will do calculation for you. But if instead of putting this K, and instead rather if you join this wall to this column and start doing the analysis, then it is just like joining the concrete and wall together as a two fixed elements, which is not the reality. Okay, so we have to be careful while modeling these elements and considering the material strength. And that is where the undergrad course also helps us, because all the parameters like Poisson's ratio, Young's modulus, bulk modulus, anything like that, we get the idea of all these things in the undergrad. And with those concepts, we have to use it in the finite element softwares. So let me give another example over here. So what actually happens in a lateral load case for partial infill frames? So when I say partial infill frames, that means the top part of the wall, top part of the frame is left open for ventilation or light purpose. And then the bottom part is constructed with the wall. So during the time of earthquake, the building, the frame may behave like the second on that one in the right with the wall. And if the wall is not provided, then you can see that making a simple skeleton structure, then the deformation looks like in the left. So if the deformation is like this in the left, but if you want to put the wall also in the model, then how can you design, analyze the structure without incorporating the existence of the masonry wall? Then it will not give correct answer, right? So if you put the masonry wall in the frame, then obviously you will get good result or correct result. But how to do that? And again, to do that, you need to know the model. You need to know the real behavior and how to model the wall element into the frame. Okay, so these are some of the things that you should know. So only knowing the software is not enough. That is my point. You have to know the real structural. Once you know the behavior of the structure, then it's not difficult to put those things together in the model. Okay, this is very important over here. So here, let's take one example. If this is a partial infill, without going for very big softwares like Mr. Bora had given some examples. of some big software, this is a very lateral loading, either dynamic or static. You can make this element like you have to know the Young's modulus of this whole wall, and then you provide this connect with the diagonal strut, as we call it as the diagonal strut method. Then the problem is if you don't make or release the moment in this junction, then the behavior will not be exactly as what it has to be done. That means if you only join this link strut at these two diagonal points, then it will behave differently. But if you release the moment over here, then it will behave again differently. And if you check it with the experimental results will be somewhat tallying or validating with the one with the releasing of the moment. So this is just one example I was trying to tell you, that if you do not know how to use the software properly, then you may get some erroneous result, which we do not want. Okay, we are using the software to get correct answer. We are not using the software to get wrong answers. That's the point. Okay, so I always urge my students or the structural engineers or all those professional practices that you must know the software's limit, the limitations, its capacity to its full swing, and then only please try to use it. Okay, so finally, my few words over here, the result output depends upon the input data. So wrongly fed data will give wrong results. This we have already discussed. And for the research aspirants, please begin with the fundamentals and only start using software to solve your problem as a tool. For example, just consider that there is a problem, and if you want to solve that problem, first, how you're going to solve that problem. Then if you consider that you have a calculator with you, okay, so let us suppose you want to add a couple of numbers together. Then if you are very clever enough or very smart, then what you do, you just start calculating in your brain, and then you'll say, okay, 2 plus 2 plus 5 is so much, so much, so much, and then you give the answer. But if the volume of these values to be added are too long, then okay, you will say, okay, the problem is adding. The problem is to be added. But if I start adding with my brain, then it may take a long time, or the answer may also be wrong. So what I will need, I need a calculator. So if I get a calculator and start using the calculator to add these values or these data, then I will get some good result. But if I add these results in a very hurry, then if I enter wrong values, then the answer that is going to come wrong. So the point is, firstly, identify your problem and think whether your problem can be solved in which way, which software is the most appropriate. And also, you also should know what is the capacity of that software, whether this software is going to do the things that you want to do or not. Just by getting the software, please don't jump into it. So this is my point, that you first know your problem and select the tool that you are going to use and use it in a very appropriate way so that the result is the most correct. Okay, so do not begin your research directly using softwares. First, make fundamental concept and methodology clear. So having said this, I'm not saying you are not supposed to use software again. I'm trying to tell you, use the software the most, because nowadays we will not be able to survive without the finite element software. It is not possible for any structural engineers like those days 200 years back, when there used to be structural engineers and they used to construct big things. But imagine they used to construct those things taking maybe 1 year, 2 years. Nowadays, what we do, we can even design structure within, few hours if you really have time, and if the problem is a little smaller one, or at the most 10 or 4 or 5 days, you can even design big structures nowadays. So this is the difference because of the finite element approach. Okay, so with this, I would say think smart for the society and use computing tools properly. Thank you for listening. Thank you very much.
Well, okay. Prachand sir, I request you to cancel your screen sharing.
Okay.
Thank you, Prachand sir. I believe the presentation was very effective for our participants. We are now going to begin answering your questions. As a reminder, you can still submit the questions. And our first question is from Arjun Aryal. And the question is, in case of rigid pavement with single mesh, do we put the reinforcement bar in the bottom or at the top? I would like to request Prachand sir to answer him. So
What was the question?
I repeat the question again. In case of rigid pavement with single mesh, where do we keep the reinforcement bar? Is that at the bottom or at the top?
Okay. So if you want to construct a rigid pavement, of course you are trying to give compression force for it, right? And if the pavement is compressed from top, then we know the problem is always the slab will buckle. You know, for example, if you have slab like that, then if you put load from top, then there is always chance that there is a buckling from the bottom, and there is elastic soil from the bottom, right? The soil is elastic. So if you compress from the top, as long as the rigidity or the stiffness of the slab is sufficient, it will resist. But after its capacity, it will try to deform. So it will try to deform and go down, right? That means there is a tendency of tension in the bottom. So we have to provide the steel in the bottom. Okay? That's the answer. Is it okay?
Well, thank you, Prachand sir. Similarly, we have a question from Subhan Shrestha, and he is asking, do we get a presentation slide? I want to notify all of you that a recorded version of this webinar will also be available later. Also, we have a next question from Bikram Vishal, and this question is probably for Prachand Mansur. And the question is, how to select single diagonal strut or double diagonal strut for wall modeling? So I repeat the question again. How do we select diagonal strut or double diagonal strut for wall modeling? Prachand sir.
So, okay, if I understood it, his double diagonal strut means like cross diagonal, is it or not? Can you ask him? Is it cross diagonal or two braces in one parallelly? Please, can you ask him?
Well, meanwhile, we'll go to the next question. I request Bikram Bushal to clarify his question again. So the next question is from Dinesh. And the question is, what are differences in using implicit and explicit solver? In which case we use implicit or explicit solver? And the third question is, does experimental results provide—
To whom is this question?
Sorry, sir?
To whom has asked this question?
This is a question from Dinesh. We don't have his family name.
I think this question goes to Rajendra because he was talking about explicit and implicit things. Yeah.
Well, yeah. Okay. Rajendra Bohra, please prepare your.
Generally, regarding the implicit and explicit solver, if you have to solve some static problem, we prefer implicit solver because in the implicit solver, general philosophy is that force is equal to deformation times stiffness, and that is the generally we prefer in static problem. And in explicit, we prefer dynamic equilibrium. So if you want to solve some dynamic problem like dynamic time history for earthquake or blast or impact, then we go to the explicit solver.
Well, is that all, Rajendra?
Yeah, I think that's all.
Well, okay. So back to Prachand sir. Bikram Bhusal clarifies his question, and he says it's a diagonal model, cross diagonal model. So the question now,
cross diagonal.
Yeah, how to now select single diagonal strut or double diagonal strut for wall modeling when we have a cross diagonal model?
Okay. So there are situations where and how to deal with these kind of braces. For example, if you would like to do, pushover analysis, maybe single diagonal would be the best one if you are doing the pushover analysis. And if you are doing the static analysis, also single diagonal would be the best one. Okay. And if you are doing the dynamic analysis, then what happens is the one element which is diagonal in one direction will be again at one instant, if it is compressive at one instant, and when the loading is the vice versa. That means if one directional load is from the left, at one instant the diagonal will play compressive, and the other time when the loading is from the other direction, the same compressive element will become tensile element. And the element that is diagonally placed, which was tension in the beginning, it was in the tension, becomes compression. So at that instant, these two diagonal crosses will keep on switching their tensile as well as compressive loading into it due to the application of load. So it depends upon whether if you have provided diagonal braces in as a cross, then if you apply dynamic loading as a to and fro motion, then the two diagonals would be more appropriate. Even then, if you put one diagonal and then give dynamic analysis, even then for research purpose it is okay, because in the case of research what we do is we try to find out the maximum force that a wall can take during the force earthquake. So if you can find out the maximum force that the wall can take, and that is sufficient, whether it is in one direction or the other direction, because the point is if you trying to put the brace in as a diagonal when the horizontal load is from this, the force is on the roof is in this direction, then if the strut is like that, then this strut will be feeling compression, right? But at another instant, when the loading is coming from this direction and the strut was like that, then this strut will behave like a tension element. So it will not work well instant. But we are not concerned about it. We are more concerned whether the wall is going to take compressive force or not when the loading was coming from the left direction. So the idea is you have to know which is what you are looking for. If you are looking for the maximum force, one direction, one strut is good enough. If you are looking for dynamic force, two direction, then you need to provide strut like that. So this is the point, okay? It depends on your objective of research.
Well, okay, there is one more question for Pachan sir, and it's from Jayana. And the question is, which software did you use for diagonal strut? It seems 2D analysis. And how do you go for 3D for struts? Masonry stiffness? I guess it's a question. Which software did you use for diagonal strut?
Okay, I use SAP 2000.
Okay, region Jayana. So Prachan sir uses SAP 2000 for this. I think your question is not very clear. So we would love to answer you again if your question is a little more clear. So meanwhile, there's a question from Lalit Bhatta, and probably question for Prachan sir again. And the question is, for strut and tie model for masonry infill in RC frame, do we need to perform nonlinear analysis, or we can simply perform linear static or dynamic response spectrum analysis? This is the first question. Second question is it good to consider the stiffness of masonry infill in RC frame? So to you, Prachan sir.
Okay, so the first question, so which method is good? So it's a very, it's a question depending upon the requirement. If a student or if a person wants to know what is the thing that you want to know only for linear analysis, then you get the linear result, which is not the reality. which is not the reality. It will give you the maximum capacity of the structure for the first breakage. That means first failure will be obtained from linear method. After that failure, the structure will not behave linearly, and then the result that whatever we get will not be correct. So if you want to go for the nonlinear again, then you have to do the nonlinear analysis. And if you do the nonlinear analysis, then you will find out to the level when the structure starts failing, and then to the level when it again degrades up to the breakage. Okay. So it depends upon which you want to do and to what extent you want correctness. So of course, the structures never behave linearly, because at one instant, obviously the elastic limit will be off. It will go beyond the elastic limit and the plasticity will be occurring, right? So if the structure reaches the plastic stage, then obviously linearity is no more remaining, and we have to do nonlinear. But you see, again, I will tell you, it does not mean the linear analysis is not acceptable. That's because we always try to know the real behavior of structure to the elastic limit, firstly, because this is what we teach to the bachelor undergrad level student also. And beyond that, we teach it to the master's level student. But even then, the entire world is using the undergrad student to design, to do the construction. Everything is done according to it, because there may be safety factor available for the limit working stress method. You know, for the working stress method, we only use up to the elastic limit. So even then, the structures are acceptable. That means we are making our structures safe. The concern is to make our structures safe. That is one part. To do the research is another part. To do research means to get into the depth. What actually happens is something else. What we will do is something else. Okay, so that's why which method is correct or which method is wrong, that is not the point. Why you are doing it, what is the thing that you looking for, that is more important. Okay, this is the idea. That's for the first question. Now for the second question, can you repeat the second question?
Give me a minute, sir. The second question was, is it good to consider the stiffness of masonry infill in RC frame?
The stiffness of masonry infill in RC frame, that would be wonderful if you can find out the stiffness of the masonry wall. And that is the most difficult thing so far, in my opinion, to find out the stiffness of the masonry infill. Obviously, the stiffness of masonry infill may be obtained by doing the experimental work, and from the experimental work, you can find out the stiffness also. But if you want to do the modeling, then again, that's the big problem. So a lot of people have done this for full infill wall, obviously, but when it starts coming with the one with the opening, one with the door, one with partial infill, there are some, again, a lot of gaps still remaining, because there are many uncertainties. Okay, so if you want to use the stiffness if you know the value of stiffness in the frame of the wall, that's just splendid. It's good, but the point is that's the most difficult part in the masonry infill structures.
Thank you, Prachand sir. Meanwhile, I have brought Mr. Praveen sir into the frame, and he has personally sent me a message, and he says he has recently written a book in finite element analysis and has been published by Elsevier, and he is very happy to share the ebook to the interested one for free. So Praveen sir, you'll have 1 minute to tell about your book. Please unmute yourself, Praveen ji.
Vin, let's unmute your speaker. Okay.
Hello, hello everybody. My name is Praveen Padak, and my regards to Professor Prachanda sir and Susan sir from here. I just want to tell something about myself. Rajendra knows me as well. Susan sir knows me as well. I'm currently in Australia working as a professional structural engineer, but I got opportunity to do some research in finite element analysis when I was doing my master's degree in University of New South Wales. And after I graduated from University of New South Wales, I also got the opportunity to author a book with a professor from Western Sydney University and another professor from RMIT here in Melbourne. So, and I'm happy to share that book, which is titled as a finite element analysis of reinforced concrete beam, which basically includes the basic concepts and the basic requirements for the finite element analysis, which is, as we discussed, I think Rajendra also discussed about this, and Prachanda sir also discussed about that. Like basic is what materials we want to use and what elements we want to use and what's our requirement, what we want to analyze it from that, what's our objective. So it's currently being, I think, in market around $200. If you see that in the Elsevier website. So for all my respected seniors and all my colleagues around in Nepal and all my juniors who are aspiring researchers in Nepal, I'm happy to share that ebook. If you can send me the email, so I'll request Dixit to collect those email address for me, and then if you can send me all the interested aspiring researchers email address so that I can send them the ebook from my side. So yeah, anything. I'm not the expert. Again, I'll tell you again, I'm not the expert, but I've tried to, along with other two professors, we tried to include basic concepts and some coding concepts. And it is done in Ansys. Some of the examples are there for the finite element analysis in Ansys. So Ansys. So anyway, so that's my, I thought like there are so many interested people around there and looking forward for the so much of information. So I think my book will be really helpful for the interested one. And thank you for everybody to listening. And I'm very grateful of Prachanda sir and Rajendra and Susan sir as well to see you there in the online. Thank you.
Thank you, Praveen sir. So he has requested all the participants who are interested in reading them, please send an email to our email ID, not to the chat box here, because this is a temporary one and I'll be like busy with other things. So I request all of you to send an email to EEREC2017@gmail.com and I'll be forwarding that to Praveen. So the next question is for Rajendra sir, and the question is, does experimental results provide concrete damage plasticity behavior such as dilation angle, viscosity parameter, and yield stress? If no, how can we assign such values in finite element analysis softwares?
Well, actually, personally, I never measured those parameters by myself, but as far as I think, we can measure them by using triaxial compression. And nowadays, there are so many literature about that, and we can correlate based on even just compressive strength and tensile strength of concrete to those parameters. Well, we have, regarding the how can we assign those values in FEA, there are so many material models, they directly accept these parameters and some automatically calculate for us. So we should look at the theory manual of what software we are using.
One more question to Rajendra Bohra, and the question is, so will there be any difference in result obtained from cracked software other than the genuine one? So this is
I think it's quite difficult to answer for me.
So can Prachand sir help Rajendra in this regard? The question is from Sagar, and the question is, I see a lot of people, even professionals, are using cracked software for the analysis and design. How much can we rely on the results from this cracked software?
Now it's it's a very difficult question, because to know whether the cracked softwares are giving some problems at times or not, this has been identified sometimes, because sometimes we get some strange results with the cracked softwares. But these kind of results may be due to some other reasons also. I'm not very sure. But of course, at times when cracked softwares are used, we get little weird answers, weird results at times. In different cases, I've also felt it, but I'm not very sure whether that is because of it being cracked or because of the input being erroneous. I'm not very sure, but most of the times. For example, let me tell you one example over here. Okay, so most of the students, when they use the software, obviously it is the crack softwares, right? So when they do analysis for framed buildings, and one thing that I've felt very weird is when they analyze frames, they find it perfect. All the results are coming perfect as long as there is no cantilever slab protruded or projected from some locations. And at the instant when they model the frame inclusive of the beams and the slab, which are protruding or projecting from that frame, I'm talking about the 3D frame, then at times these beams are, getting failed. They say, they complain me that, sir, this analysis, if I remove the cantilever, the structure is safe. If I put the cantilever, no matter how big the beam I provide, the structure result is getting failed. The beam is failed. This is quite weird. And I asked them to, okay, check removing it. And when they remove it, that structure is safe. When they again put it back, again is failed. So I don't know whether it is is due to the crack software or some limitations or the method of application of the slab is incorrect. So it's not very sure, but some problem is there. This is all I can say now.
Well, thank you, Prachancha. And there's one more question from Bikram Bushal, and this question is probably for Prachancha. And this question is related to NBC 105. I would like to notify all the participants here that Prachancha is strongly involved in designing the Nepal building code recently as well. And the question is, in 1893, 2002, column beam ratio is given as greater than 1.1, but in 2016, its value increased to 1.4. But NEC 105 suggests 1.2 recently. Which value makes sure the strong beam column weak beam concept? Oh, sorry, I didn't get what he means. NBC 105 suggests 1.2 recently. Which value makes sure the strong column weak beam concept? So do you have any idea about this, Prachancha?
Yes, of course. Firstly, to go into this, I may have to take a little bit of your time. Okay, so that means I need to be a little elaborated. Firstly, the students or the engineers or the users must know what is a strong column and weak beam firstly, right? So when we say strong column, weak beam, most of the people consider like the size of the column. If it is large, then it's strong. And if the size of the beam is small, then the weak beam, or if the beam size is more, then it's more, the beam is strong and column is weak, something like that. But let's not understand it in that way. Okay. So firstly, what we should understand is while we analyze the structure, then just simply understand like there is a frame, one bay frame, and one, let's imagine a football crossbar, okay, football pole. That means a pillar, two pillars, and a beam. So if you and fixity in the bottom. Now if you take this as a frame and you start analyzing. Okay, so if you consider this as a structure and you apply UDL from the top, then you will see some kind of bending moment diagram in the beam, okay, with the negative fixed end moments. And also you will see the bending moment diagram in the column, something like some diagonal. Okay. But you have to understand is the bending moment in the column and the bending in the beam, they should be same. They will be same. Until they are same, this is not equilibrium. So in equilibrium, both the bending moments are same. That is the science. That is the science. But that means the beam will be provided with the quantity of steel that is required because of that bending moment. And the column will also be provided with the quantity of steel depending upon that bending moment. Now, if we start providing the exact quantity of steel that is required by that particular beam in and that particular column. But what we want is, we want the column to last longer. We don't want the column to fail first. We want the beam to fail first. That's the idea during the earthquake. So if we want the beam to remain, to fail first, then obviously one element should be stronger than the other element. But you know, both of them were having same bending moment for equilibrium. I'm not talking about the different combinations, okay, load combinations. I'm just giving you a very small idea how this is happening. Like if you provide steel 20% more, let us just imagine 20% more than that is actually required by that column. Then what happens? The column becomes stronger than that actually needed the steel for, right? But if you start providing, again, similarly, the more steel in the beam, again, you are making the beam stronger. So this does not work. What we want is the beam, let the beam be as strong as it was required to be strong. Then you provide the steel, because it's a flexural element. If you provide more steel in the beam than that is required, then you are making the structure over reinforced. But in the case of column, there is no problem. You can make the column, provide the column with more steel than that is required. And while doing so, you are making the column stronger. But so in this way, you are making the column stronger and you are making the beam to the same strength than that actually was required. So in one way, you are considering strong column and weak beam. That is a very general way of considering the thing. To calculate it, you have to understand if it is the junction of a column and a beam, okay, then in these two sides of the beam, the moments in the beams are coming to sum of moments from the column, and the sum of the moment from the two beams will be in equilibrium. So they are equal in engineering, or let's say in science. But since we are engineers, what we do is we want to make our structures not only correctly calculated, but also to make it safe. So correct calculation is equilibrium. To give safety is beyond the equilibrium. We have to provide some more strength. And if we provide more strength to the beam, then what happens? The beam becomes over reinforced. And we don't want the beam to be stronger than the column. So we provide more steel to the column, and we again do the calculation, and we find out whether if we give more than 20 times, that means 20% of the steel, or let's say strength of the bending moment in the column, then what we do is we are saying the column is stronger than the beam. The point is whether 20% or 10% or 15%, it is all dependent upon the country to country code. Okay, some country will have a lot of faith in their construction material, a lot of faith in their construction people. So they provide lesser factor of safety. Some country will feel like, okay, no, the material is not of good quality, the quality control is not good, the workmanship is not good. So we should put more factor of safety. So depending upon that, this 1.2, 1.4, 1.1 is provided. So I think I made myself clear.
Thank you, President, sir. We have next question from Naresh Subedi, and he is a PhD candidate at Tokyo Institute of Technology in Japan. And the question is to Rajendra Bohra. The question is how to model multi-point constraint between a control master node and set slave nodes in LS-DYNA. What is the method used to tie completely fixed two parts together in LS-DYNA? Please, Rajendra Bohra.
Well, generally, there are two methods to completely fix two parts. One method is very conventional, like we generally merge the node at the interface, and that may not be feasible in all the cases if we have different meshes into different parts. So it used the contact, the most widely used contact for this kind of scenarios, contact surface to surface tied in LS-DYNA, and we can fix two parts by using that contact.
Well, thank you, Rajendra Bohra. The next question is for Prachan sir. And the question is from Tekan Pandit. The question is, when we do pushover analysis for infill RCC building in SAP 2000, where we have to put the nonlinear behavior for the infill, in such case, we have to put stress-strain relationship or force deformation relationship. My question is that when we put stress-strain value, software asks to put hinge length. In such condition, what is the value of hinge length for infill? Prachan sir.
Hinge length, I don't understand by hinge length. Does it mean by diagonal length, length of diagonal?
Taken.
I think it's a plastic hinge, location of plastic hinge maybe. Near to joint.
Well, okay, I request.
Please ask the question to him again.
I request Tekan to elaborate his question again. So we'll come back to him again. And the next question is from Vikas to Prachand sir. And the question is, in pushover analysis, while superimposing the response spectrum curve for new NBC 2019, the shape of the descending curve looks sort of a concave downward, opposite to the regular shape. What could be the possible reason in pushover analysis? Question to Prachand sir.
I think the figure should come same for all the response spectrum, because the response spectrum, only the values are different, but the behavior is all the same. So the response, due to the change in the response spectrum, it will not make effect in the the curve behavior. Of course, the values may be different, but the curve behavior will not be different, because it's the same. Only thing is you make the response spectrum value only different. Everything is same. All around the world, the response spectrum is, the core nature is same, because there is always constant velocity, constant acceleration, these ranges. So it's always the same.
Tekan Pandit says it's plastic hinge length in the last question.
In the last question means the previous question.
Yes, in that condition, what is the value of hinge length? What is the value of plastic hinge length for infill?
I'm not very sure about it, because I have to look for those things, because you see, if he is asking about the plastic hinge length used by the what you call it as a pushover analysis software, then I'm not very sure what he is actually looking for, because in general, when we provide the element, the model, what we do is we simply we give the length of the frame, or the dimension of the frame, and we also provide the dimension of the diagonal strut. And then the point is you have to make the two connections moment release. That's the point. Okay. And once you do that, the remaining parameters that are asked by the pushover analysis software are something else. Okay. This is something else, but I'm not very sure what he is looking for, because according to my work, I didn't do the pushover analysis using the diagonal strut like that. I did it for SAP 2000 only, directly for the analysis, which was meant for professional engineers, not for researchers. Okay.
Thank you, Prachan sir. I request Tekan Pandit to send all his questions via email, and we'll try our best to reach you with answer as soon as possible. So that's all about today in the question and answer session. And it looks like we have answered all your questions. Thank you, Rajendra Bohra and Dr. Prachan Pradhan. And thank you everyone for attending today's webinar. If you have any other questions, please contact us via email, and we'll try our best to answer you. Finally, on behalf of EEREC, I would like to request the chairman for today, Sujan Tripathi, for his concluding remarks. Thank you and have a great rest of your day. Sujan sir.
Thank you, Dikshit. Hello, everyone. Good morning. First and foremost, I would like to express my heartfelt gratitude to all those who are participating in this program. Similarly, I would like to express my heartfelt thanks to a renowned figure in the field of structural engineering, HOD of Civil Engineering Department at Kathmandu University, Associate Professor Dr. Prachandaman Pradhan for presenting keynotes and sharing his valuable experiences and knowledges regarding to today's presentation. Also, I would like to give thanks to a prolific researcher, a PhD scholar at the University of Melbourne, Mr. Rajendra Prasad Bohra, for his informative presentation on the systematic applications of finite element-based advanced software in the Nepalese context. As we all know, advanced software can play a great role to save the time of structural analysis and design, and also the quality of design work. Design software are also beneficial to reduce the short-term and long-term project cost. Nowadays, anybody can get the software and can use it easily. However, the major questions are that, are we using the design software in a real way? Do we have the basic knowledge about the software that we are using? Are we able to use that software to solve the real and complex problems associated with our community? I would like to say thanks once again to the valuable presenters for raising these genuine issues from this event. Similarly, I would like to appreciate to the Managing Director of EEREC, a PhD scholar at University of Sydney, moderator of this program, Mr. Dikshit Babu Nepal, for his role to give the shape of EEREC webinar series program. Next, I would like to say briefly about the EEREC and about the upcoming program. EEREC is a research organization which was established in 2014 AD by a group of professional researchers who are working nationally and internationally. After establishment, various activities related to the engineering field has been conducted by the EEREC. In short, the main objective of this organization is to boost up the research culture and to establish the cost-effective indigenous techniques to solve the complex engineering problems associated with our society, and also to conduct various activities to transfer the knowledge and experiences which are found from our research works. Now, I'm going to presenting appreciation certificate to the keynote speaker, Professor Dr. Prachandaman Pradhan, and the presenter, Mr. Rajendra Prasad Bohra. Here, I'm demonstrating these certificates virtually. So I'm going to share the screen now. Okay. I think it's visible now, right? Is it visible?
Yeah, it's visible.
Okay.
I request you.
Yeah, this is for the
full
yeah,
screen.
this is for the this certificate for the keynote speaker, today's keynote speaker, Professor Dr. Prachandaman Pradhan. And then next for the presenter, Mr. Rajendra Prasad Bohra. Okay.
Thank you very much.
Welcome, sir. And now I would like to share with you all, EEREC is going to organize next webinar on 14th November 2020. The presenter will be an international young researcher. Program details will be released later. Before closing the program, I would like to request to all the participants for your valuable comments and suggestions. Also, if you have any queries, you can send to us without any hesitation. At last, I would like to announce that today's webinar has finished now. Once again, thank you all the participants and namaste. Thank you.